Okay, I think it's time. Sylvia, should we give it a go? Yeah, okay. So welcome everybody to the afternoon session of the second day of the ALife. I proudly present Jacob Shoemaker, who will give the first talk now. Could you share your screen, please? Who will talk about benefits of credit assignment in noisy video games or computer games, video game environments. So please go ahead.
Thank you. Yes, welcome everyone to my presentation. I'm Jacob Schoemaker and I co-wrote this paper with Karim Miras. Our paper is on the benefits of credit assignment in noisy video game environments. In this paper, we will be comparing the performance of reinforcement learning algorithms with that of evolutionary algorithms in a video game environment. The video game environment we chose was EvoMan, which is an environment written by Karim as a testing ground for evolutionary algorithms. In this paper, we've extended this framework to make it possible to benchmark reinforcement learning algorithms in the same environment. We've tried to answer the question, does credit assignment result in better performance in noisy video game environments? And the reason we wanted to explore this question is because we were interested in the advantages of the different approaches to machine improvement of an agent, which will help us understand how life learns to adapt to different circumstances in its environment. We used 4 out of the 8 environments provided by EvoMan to make sure that none of the algorithms had an advantage based on the specific environment they happen to be better at. So I'll show these environments for a bit. This is Airman, which shoots projectiles towards the agent in a repeating fashion. There's Bubble Man, which has instant defeat spikes at the top of the environment. So if you jump too high, the player is instantly defeated. There's Flashman, which approaches the agent and can freeze the screen to shoot a large amount of projectiles at the agent. And there's Heatman, which shoots projectiles that remain on the ground for a time that the agent must learn to avoid. Because reinforcement learning algorithms and evolutionary algorithms have different methods of improving, we have to make sure that the reward and fitness functions gave a similar measure of performance. And thus we chose formulas that resulted in the range of rewards obtained by a reinforcement learning algorithm over a single episode in the environment to be the same as the range of fitness values that can be obtained by the evolutionary algorithms. There are 20 sensors in total for the agent, consisting of the direction of the agent and the player character, the agent and the enemy character, the relative position of the enemy as an X and Y value, and the relative positions of the projectiles, of which there are a maximum of 8. Noise was introduced into the environment by varying the initial position of the enemy between episodes played in the environment. For each class of algorithm, we used 2 algorithms, one that we found to be fairly simple and one that includes some more advanced methods. For the evolutionary algorithms, we used a simple genetic algorithm of our own design, and we used neuroevolution of augmenting topologies. For reinforcement learning algorithms, we use deep Q networks as the simple algorithm and proximal policy optimization as our advanced network. To make the comparison as fair as possible, we ran each algorithm for the approximate equivalent of 100 generations with 100 individuals. So for the evolutionary algorithms, this is exactly 100 generations with 100 individuals. And from testing, we found that this took about 2.5 million time steps, which is the amount of time we gave the reinforcement learning algorithms to learn. Each algorithm was trained 100 times in each environment, 50 times with noise and 50 times without. And to gather data, the best performing agent for evolutionary algorithms was benchmarked every generation, and the agent for the reinforcement learning algorithms was benchmarked every 50 episodes in the environment. We can see the results of the environments without noise here. Deep Q networks, which is presented in blue, is shown to perform very poorly in all environments. We will see this recur in the noisy environments. We found out after we ran our experiments that deep Q networks take very long to start converging towards performance over that expected of random button presses. We likely didn't give it enough time to learn. We found some numbers that said often doesn't start improving until about 10 million time steps, but we only found this out after having run the experiment. Proximal policy optimization, which is shown in orange, can be shown to achieve consistent and very fast improvement across each of the separate environments. Clearly, the most difficult for this one is Flashman. The simple genetic algorithm, which is shown in green, is shown to perform fairly well in each environment from the get-go. We think this is due to generating a large set of random individuals, giving a decent chance that one of them will have a decent starting point. We can also see it improve over time in the static environments. NEAT, or neuroevolution of augmenting topologies, which is shown in red here, doesn't have the benefit that the genetic algorithm has with the initial population, as the NEAT algorithm starts out as perceptrons and needs to evolve its own topology before it can do any serious learning. It does show improvement over time in each of the environments, though it often doesn't quite converge yet within the time frame. In Heatman, NEAT can be seen to evolve avoidance behavior, which is why its value approaches a reward of 0, no health lost by the player, but also no health lost by the enemy. And after this doesn't really evolve. It shows a very large range for Flashman, and looking closer at the data, we can see that either it gets a very high score of -30, or it gets a very low score of -30, or it gets a very high score of about 90. This indicates that there's one or two important connections in that NEAT has to evolve to perform well in this particular environment. In this slide, we can see the results of the environments with noise. We can see the same poor performance from deep Q networks, as explained in the previous slide. And from proximal policy optimization, we see similarly consistent improvement despite slower convergence towards a high score. Genetic algorithms still show decent starting values. However, it doesn't manage to improve much over time in these environments. Neuroevolution of augmenting topologies only really improves in Airman and Bubbleman, but even here doesn't show very strong improvements. The only one where it really shows improvement is in Airman. So, coming back to our research question, does credit assignment result in better performance in noisy video game environments? We say yes, or at least credit assignment used by reinforcement learning algorithms can lead to much more robust performance in the face of noise, in our case. Yeah, we found that only evaluating the agent with the evaluation function makes the agent more prone to noise, likely because any agents with good performance aren't able to pass the inconsistent starting conditions of the environment. State transition used by reinforcement learning algorithms seems to deal with this better, as it can relate individual actions and positions from the enemy to actions that the agent should be taking to counter these. Future work, we think it would be interesting to run these experiments to convergence to see whether there's a difference in how long it takes for each algorithm to reach convergence, and whether deep Q networks, for example, can improve in this environment, or whether it is just too simplistic of an algorithm. It would also be interesting to see this experiment be performed in more environments than in EvoMan. It could be that this environment just happens to suit itself better to reinforcement learning algorithms. And it would be interesting to see this experiment performed with other types of noise, such as sensory noise, rather than noise in the initialization of the environment. This was my presentation. Thanks for listening. And are there any questions?
Yeah, thank you for keeping the time. I think we have enough room for questions. We have 8 minutes.
Yeah, it went a bit fast.
I would have a very, let's say, maybe naive question, because I'm not from that field. What I've learned in the past is that if you perform any form of learning or evolution on a simulator, it quickly falls into some sort of a reality gap. And it does not really create easily things that are useful then in like real physical applications. The game is now even further away from a practical application than a simulator with a physics engine and so on. So what do you say about like the applicability of these findings towards real world robotics, for example, or self-driving cars or whatever?
Well, why we think video game environments make for an interesting benchmark for experiments like this is because they can provide a large variety of environments, which allows us to test the performance of algorithms under different circumstances easily, and especially in environments that aren't influenced by the bias of the experimenter, as the environments have been created by completely separate parties, the game developers.
Mm. Okay, do you think that like the conclusions that you have drawn now by comparing the 4 different methods, that would also hold for a real world application that somehow is similar to what these games depict as a scenario that goes on? I don't know exactly the game that was used there, but like it was like a figure running around and jumping around or something. So there might be a similar physical task with a robotic arm or something like that. Would you think it holds in comparison? Do you have indications for that or assumptions?
I wouldn't say that the performance of this environment directly maps to a real world application. I think it just shows us. I think. How do I word this appropriately?
You can also word it inappropriately. So it doesn't
but
matter.
like, how do I get my point across? I think they provide decent. They act as decent benchmarks for the generalized case rather than for a specific application.
Mm-hmm. So for the idea or the concept of a task, you mean?
Yeah.
Yeah. Okay. We have a question in the chat. Thank you for answering my. Was not meant nasty or anything. It's just like from my experience, I know that simulator to reality is very tough. And
yeah,
then
of course.
the game is even more abstract. Yeah, we have one question from James. Do you want to ask your question yourself? James Stovold? Obviously not. Yeah. Okay. Have you considered taking a look at multi-level games?
So train on the level.
Train on the
like
level like you did here, and then make changes.
No, I have not. I've not done that in this experiment. The framework has actually been set up in a previous paper by Karin for trying to create a general agent that can learn from a subset of the 8 environments provided and see whether it can develop a policy that can beat all of the environments based on only 2 or 3 of the environments actually being trained in. Mm-hmm. But we haven't tried this for this paper.
Yeah, I was also wondering about the game issue. Coming back to the game question, these games have levels. Do you have a question? I see the hand raised. Yeah, Karin and Gus, you have a question.
It's me who has a question. Thank you
okay.
for the floor. So very nice work. Congratulations. But one of the essential details is whether the comparison is fair. And you said you would make it fair. And I would like to ask more details about your argument saying comparing transitions. You said you have populations of 100 individuals and 100 generations in the evolutionary approach. And you said, which is the same as the 2.5 million, what was it, steps in the reinforcement learning approach. So could you explain why these are equivalent?
Yeah. Well, it's approximately equivalent. It's not exactly equivalent, but it's purely from empirical testing. We found that the evolutionary agents tended to either be defeated or defeat the enemy in an average of 250 time steps. So after that, we multiplied that by 100 for the agents and 100 for the amount of generations, which led us to 2.5 million, I think.
Okay, yeah, thank you. But somehow it's not really what my intuition would require. My intuition says the effort, the computational effort or the learning effort should be
yes, this is actually something I did talk about in the paper because we started with the amount of data being provided to the algorithms. But during the running, we indeed found that the evolutionary agents, due to the mutations being cheaper than the calculations, the gradient descent calculations required for reinforcement learning algorithms, we found the evolutionary algorithms to run in about 1/10 of the time. So I am definitely interested to see in what the performance comparison would be with an equal amount of computational time allocated to each algorithm. But in this case, we went for data gathered from the environment.
Okay, sorry guys, we have to stop now the discussion at this point. And thank you again, Jacob, for the nice talk. And we go to the next one, which is by Thomas Wilkins and Jordan Pollock about evolving unbounded neural complexity in pursuit evasion games. Please give it a go.
One second. Okay, sorry about that.
Now it works.
Okay. Okay, my name is Tom Wilkins. My advisor is Jordan Pollock. We're with the Demo Lab at Brandeis, and this is Evolving Unbounded Neural Complexity in Pursuit Evasion Games. So some background, this should be familiar to people who've studied evolutionary algorithms. We have an organism type. So this is some general computational system, an individual, which is an instance of the type, sets of individuals, the population, equipped with some operators for selection and variation in order to reproduce. We also have interaction functions, which we have two different categories, which are cooperative, in which the interests of both parties are broadly aligned, and competitive, in which they are misaligned. The domain is a set of interaction functions, and we have a new term, the ecosystem topology, is when we have a collection of populations and interactions represented as some sort of graph. And so here we have an orchid mantis in a competitive relationship with some pollinating butterflies, which are in a broadly cooperative relationship with a species of orchid. We also have some additional terms, the complexity metric, which is some function of an individual, which yields a value based on either genotypic or phenotypic features, and unbounded complexity growth. So this would be a property of an ecosystem, which is true when the average individual complexity reliably increases over an evolutionary timescale. In addition, it must be greater than that produced by genetic drift. One thing, study, we believe, could lend insight into open-endedness, but the two concepts are distinct and should not be confused for the purposes of this talk. So the prior work here is the linguistic prediction game of Nick Moran, who is a former member of the Demo Lab, in which, in this scheme, the organism type was a deterministic finite state machine. So we see some examples of those on the right. The interactive domain is a prediction game, similar to the iterated prisoner's dilemma, with both cooperative and competitive varieties. The selection method employed was fitness proportionate, which we will term roulette, and his complexity metric was a state count of the minimized DFSM. So after minimizing it, stripping away unnecessary states, how many there are in the machine. So the results of running his experiments, you can see there's a grid of different ecosystems, which he investigated here, along with a corresponding grid of results of complexity growth, in this case over 100,000 generations. The results of his experiments showed that solely competitive and cooperative ecosystems fail to outgrow the control. So for instance, the two competitive flatlines, the three species competitive flatlines, while the cooperative group grew at a rate roughly equal to that of the control. However, mixed ecosystems, which feature a combination of both cooperative and competitive relationships, such as 3 mixed and 4 mixed, did show evidence of unbounded growth in one or more of the species. And in particular, this growth was shown in the cooperative species. So the green here corresponds to species C, and the red and green here correspond to C and D. Now, Nick had some hypotheses for this. First, that convention chasing, which is a classic coevolutionary pathology, suppresses growth in the competitive ecosystems, and that the reason for the growth in the cooperative species might be because it evolves mechanisms as a buffer against cycling between the other two. He further proposed that these dynamics might hold more generally and be useful in other interactive domains. So to test these hypotheses, we introduce a new interactive domain called the collision game. So this is a parameterized pursuit evasion game, which takes place on a one-dimensional number line. So some of those parameters might be the number of time steps, its finite horizon, how far apart the players start. And in on each time step, each entity will move some distance forwards or backwards and emit some scalar communication value. If the two intersect, so if the one on the left goes further to the right than the one that starts on the right, we mark it as a collision. But if they fail to intersect by the end of the episode, it is an evasion. Our organism type is recurrent neural networks, which are similar to neat networks, but they reproduce asexually, so they're simpler. And our complexity metric is the number of connections in a pruned network. And so to give an example of that, we have two input nodes here, the normalized distance and the communication value of the other agent, a bias node, which just owes output some constant value. And then the yellow and gray nodes are hidden nodes. In this case, the yellow nodes and purple connections would be pruned because they are incapable of influencing the output. These are the red nodes right here, which would be the movement and communication values. And so in that case, we would score this with 5, counting the number of black connections. We have a number of different interaction functions in this game. The first two are affinitive and avoidant, in which both are rewarded for collision and evasion respectively, and adversarial, in which one is rewarded if collision occurs while the other gets the opposite. And so under our scheme, we would call affinitive and avoidant interactions, broadly speaking, cooperative, while the adversarial one is competitive. Players begin the game without knowing the other's identity or incentives. And so the ecosystems we investigate are similar to the ones that Moran used, but with some differences to make them better tailored to our domain. For selection and variation, we employed 2 different selection methods to compare them: roulette, as well as the discovery of search objectives, or DISCO method, which is more recent, having been published in 2017. The virtue of DISCO is that it can identify and promote organisms with unique skills, even if they have lower scalar fitness values. So it's specially tailored for coevolutionary problems. The basic idea of how it works is this interaction matrix, in which the letters here correspond to different organisms within a population, and the rows correspond to their interaction outcomes against members of other populations. What we do is we cluster along the columns of the interaction matrix and take the centroids of those clusters in order to form what's termed a set of derived objectives, which then can be used with a multi-objective optimization algorithm. We use X-means clustering to automatically determine the number of clusters, and then NSGA2 to select the individuals for the next generation. Individuals reproduce asexually here, connections are injected with Gaussian noise, and then a new connection or node is created or deleted with equal probability. For our experiments, the first experiment is a control experiment in which the red line here is the median with upper and lower quartiles of the total number of connections averaged across all members over 20 different trials. In this case, the blue line represents the expressed connections, which is just another term for the pruned connections, which we actually would use as our complexity metric. From here, we see the genetic drift leads them to grow over time, as the number of connections is bounded at 0. We can't have negative numbers of connections. But nonetheless, the number of pruned connections remains small and relatively stable as a benchmark comparison. The next set of experiments look at the 2-species competitive and 2-species cooperative ecosystems, in which case we can see also comparing the results of the 2 different selection techniques. We see that in none of the cases do we really see signs of unbounded complexity growth as in the prior experiment. We do notice some differences, namely that the roulette groups exhibit higher variance compared to the DISCO groups. And one reason for this might be that the optimal solutions for both ecosystems are relatively trivial, and DISCO may do a better job at sort of mitigating the risk of unnecessary connections. To show this in action, I'll show a visualization from a particular trial in which on the left side, you will see a single host paired with many different interactions with 20 randomly selected parasites from that generation. So you can see on the left, so each one of these is a different interaction of the game, and you can see the time step increasing right there. You can see that the host simply flees, as naturally it would be disincentivized from colliding with the parasite. And the parasite has, no other reason other than to chase. So in this case, the host completely succeeds and evading the parasite in nearly all cases. Now, you might have noticed that some of them had a different color. And so here we can zoom in on a particular interaction and also compare the network graphs. So we can see that the host has just a single connection running from the bias node to its movement node. In this case, the state of the node is represented by its color, where blue is a value close to 1 and red is a color close to -1, as well as the output of the connections. We can see its input node reflects the color of its partner. The parasite also has a connection running from the bias node to the movement node, and also a sort of extraneous connection running to its communication node, which obviously is not very efficacious in this scenario. So for our experiments, well, moving on from that to the 3-cycle ecosystem, this one is a more intricate mixed ecosystem where we have an affinitive relationship between the host and symbiote, a competitive relationship between the parasite and the host, and an avoidant relationship between the symbiote and the parasite. So now that introduces an element of risk, as neither can just sort of blindly charge forward. It risks being punished. This leads to different dynamics in the observed complexity. We see that the roulette group grows fairly steadily early on, but then seems to plateau halfway or maybe 3/4 of the way through the trial. The disco group, on the other hand, shows clear signs of unbounded growth as it continues to grow throughout the duration of the trial. To get a sense of the differences in the phenotypic expression of their interactions, we will now take a look at one host versus 20 selected symbiotes that received high fitness values. And from here, we can see that there's a great deal more variation in behavior, as well as variation between different interactions. We also can notice some patterns. For example, the flashing of the host ceases once it begins moving to the right. And it succeeds in colliding with symbiotes a majority of the time. We also can visualize the graphs, and we see that they indeed are more complex. We can see that there are rapid cyclings and flashings of the internal states of the nodes and changes in the overall sort of topologies of the connection outputs. This one does end up succeeding in colliding and receiving reward just in time. We also will look at the same host versus 20 parasites from the same generation. We see here that there is different behavior exhibited by the parasites. There's a sort of oscillatory behavior if it fails to lure the host to it, as well as some of them continue to chase. We also can see that the host manages to evade the parasites more frequently than it does the symbiotes. And we can see here that the interactions between the networks are also rather complex. And it's also somewhat amusing because the host actually ends up chasing the parasite off the screen in this particular interaction. Now we'll look at the final pairing of one symbiote versus the same 20 parasites of the previous visualization. And here we see that the symbiote actually succeeds in evading the parasite in nearly all cases. There's one interaction right here where there's a collision, but in this case, it's in their mutual interest not to collide. So clearly there's some form of effective communication happening within the complexity of the networks. The final experiment we'll look at here is the comp cycle ecosystem, in which this is a 3-species fully competitive cycle. X competes with Y, competes with Z, competes with X. If we look at the results of the complexity growth, we see that the roulette group does seem to support the hypothesis of Moran. It has the lowest observed complexity of all of the different configurations tested. However, the disco group achieves growth comparable to the one we just saw. So clearly, these kinds of systems are sensitive to what selection methods you employ. There's not enough time to do a full overview of the competitive cycle, but we'll just look at one interaction just to get a sense of how complex these networks can grow in 25,000 generations. And so one reviewer brought up a fair objection. How do we know that all this apparent complexity isn't just bloat? And so what we did was we performed an experiment, taking all populations of all trials of the 3-cycle disco ecosystem, and then performed a pruning experiment where we progressively prune, increasing the pruning rate using a variety of heuristic pruning methods, and then reevaluate the pruned individual against all of the original members of its environment. And we see that the average fitness drops as the pruning rate increases. And so there's a connection between this complexity metric and the fitness of the individuals. So it's a meaningful metric that is possibly appropriate for this particular domain. So in conclusion, the broad phenomenon of unbounded complexity growth is indeed reproducible, and ecosystem topologies strongly influence behavior patterns. However, the choice of selection method may have profound impact on the complexity growth in such systems, and it's unlikely that the previous findings are truly general. So for future work, deeper analysis of network structure and interactive dynamics is needed. We also need to better understand the effects of selection methods on complexity growth. We know why DISCO should make it improve, but we don't know exactly how it does so. It would be worthwhile to study trends in more detail over evolutionary time, as well as to test the linguistic prediction game to see whether it exhibits similar sensitivity. And also, this general framework could be extended with additional interactive domains. That's all. Thank you so much.
Okay, thank you very much. Great talk. Perfect timing. Do we have questions in the chat? Or just raise your hand and speak out, please. Okay. While we are waiting for questions, I would have one. Did I get it right that this DISCO method is something like, could we say, genetic novelty search or something like that? Did I get that right?
Yes. So it sort of has a number of different levels of diversity maintenance within it, both with the clustering of identifying different skills, as well as NSGA2 has sort of a built-in diversity preserving mechanism with the crowding technique. So it has virtues, especially in coevolutionary domains, where the objective function is so slippery.
Mm-hmm. And as a biologist, I have to ask, is there a relation to nature? So something like mate choice, that was my first guess.
Yes, that's the analogy that I used in the paper, is that it's analogous to a courtship ritual, was how I described it. Mm. And so in this case, you can see, you were making decisions whether or not to close some physical distance based on movements and communication, which we observe all throughout the natural world.
Mm. Yeah, I found it interesting. You already answered a question that I had about, like, could the genome size just be bloat? And you made an extra analysis about that.
Well, I thank the reviewer for bringing up that point and prompting us to.
I was not the reviewer. I just had the same the same idea while I was listening to your talk. But I was asking myself, how would you measure complexity directly on the genome? Something like compressibility, or in the resulting behavior, that you look at trajectory and then look at compressibility of that trajectory, or any thoughts about that?
Yeah. So that's another vein of discussion. There are many areas of future work here, because these systems, frankly, are poorly understood, even after making them. And so one possible avenue that we've been considering is using statistical complexity, possibly of the trajectories. But it's challenging because they're multidimensional and there's a lot of data to go through. One point that I didn't have a time to really drill in this talk is the diversity among trials, where each trial you end up with very different graph topologies of the neural network, as well as very different patterns of behavior. And so there are literally thousands of data points. Well, more than thousands. There are many data points to wade through here.
Okay, thank you very much.
Okay, thank you.
I think we have no other questions, and we have to carry on with the next talk, which is by Federico Pigozzi. I hope I pronounced that correctly.
Oh yeah, it's fine pronunciation.
Almost, at least. Hi.
Oh, it's good.
Could you share your screen? Yeah, perfect.
So, okay.
Yeah, so just give it a go.
Yeah, thank you. So, hello everybody, my name is Federico Pigozzi, and today we will talk about a new paradigm for modeling softness in embodied agents, in virtual agents, relying on pressure. And if we go to the motivation, what we discover is that nature is soft. Softness is indeed one of the greatest gifts of Mother Nature, and indeed, as we all know, the vast majority of living beings are made mostly of soft tissues. And here we have a tremendous example that is Lacrimaria protozoan, a genus of protozoans that can grasp hard-to-reach prey using their soft flagellum, as we can see these. And this is a great instance of embodied cognition because there is no computation happening at all. I mean, it's just a unicellular organism. And if we move on to robotics, what has been happening is that a new generation of soft robots has sprung up. And these soft robots, by virtue of their softness, promise us to achieve many interesting feats, many interesting properties, like, for example, shape change, reconfigurability, but also safety, fault tolerance, recovery from damages, and so on. Still, if we look at the current state of the art in soft robotics research, what we discover is that the simulation and optimization of soft agents pose unique challenges. In particular, non-analytical methods exist for the modeling, since soft tissues imply infinite degrees of freedom and, in general, harder to simulate dynamics. At the same time, the embodied cognition, which posits a deep entanglement between the brain and the body of an embodied agent, let it be natural or artificial, makes any co-optimization of brain and body very difficult, arduous, since the body shapes the optimization landscape for the brain in a non-trivial manner. And moreover, according to the literature, effectively achieving shape change for soft robots, for soft agents, is still an open issue. It is still a nascent field. So as a result, the main question we set out to answer in this work, and its main contribution, is developing a novel formalism for the study of soft-bodied agents, namely pressure-based soft agents, that promises us to overcome all of the shortcomings I outlined so far. If we look at the existing literature, we discover that other soft agent paradigms do indeed exist. In particular, the voxel-based one and the integrity-based one. In poor words, the way these formalisms model softness is, on one side, in the voxel-based formalism, each voxel is made up of rigid bodies placed at the corners, connected by springs, and so this overall allows for modeling softness, whereas in the integrity-based, we have a structure made up of cables that are in tension, juxtaposed with rods that are constantly under compression. But as we can see from these brief descriptions, is that both formalisms still rely on an internal structure of rigid elements, and as a result, this limits their ability to change shape. In this work, we borrow from the field of computer graphics, where other formalisms for the modeling of soft bodies do exist. And in particular, we borrow the pressure model of soft body simulation from 2003, which has been used quite a lot for modeling soft bodies, like, for example, balloons or cloth, as we can see from this picture, from this video. And we try to optimize the structure of this morphology in an artificial intelligence, in an artificial life context. And in particular, what we do, so as far as the modeling is concerned, as far as the mechanical model is concerned, we define the morphology of a pressure-based soft agent in the following way. So here we have a depiction. So the blue is the ground, so it's like an immovable object. And this funny thing at the center, so this new visual creature is indeed our pressure-based soft agent, which is composed of an envelope. It is surrounded about an envelope that is made up of rigid bodies, that is the red squares here, and these rigid bodies endow the overall body with a mass. So they endow it with a sense of embodiment, and they allow it to collide with other objects, as well as defining what are its boundaries. These red masses are connected by springs, that is the white strings here in the simulation. And springs are necessary because they model softness. Springs can oscillate, and so as a result, they allow the overall body to assume an infinite gamut of shapes. And finally, in the simulation, we model gas existing within the envelope to exert pressure from the inside. Why? Because otherwise, if there were no gas exerting pressure, this envelope would simply collapse as if it was clothed. And it is thanks to internal pressure that the agent has a structure. The agent can sustain itself and thus accomplish many different tasks. Indeed, here what is happening is that we are constantly decreasing pressure, and the envelope collapses. But then we increase pressure, and as we can see, the overall body has a structure. The agent has a structure and can thus accomplish many different things. Having said so, what kind of questions do we want to investigate for this work? And given the context outlined before, first of all, we want to understand whether we can optimize pressure-based soft agents for a given task. So we want to understand whether they can show a minimal level of cognition. But at the same time, we also want to investigate whether we can effectively exploit shape change for this kind of robotics agent, because, I mean, that is the hallmark of soft robotics. That is basically everything we've been talking so far about. And to this end, we equip our agents with sensing capacities so that they can participate into a control loop, into a reinforcement learning loop, and they can interact with their environment and solve complex tasks. And in doing so, we equipped masses with sensors. In particular, we use touch, velocity, and the relative position with respect to the center of mass sensors for each mass. And we also equip our agents with a controller that is like the brain of the agent. It is in charge. The controller takes as input the sensor readings, concatenated, so we take the sensor readings for every mass and we concatenate them in one big array. We feed those to the controller that processes them to output an actuation. I will detail actuation in later on. And in particular, we instantiate the controller with a plain vanilla multi-layer perceptron that is an instance of a closed loop controller and can thus exploit sensors. But we also rely on optimization. We optimize the controller parameters, the weights and biases of the neural network of the multi-layer perceptron with CMAS, that as you may know, is an established numerical optimizer. But in theory, any numerical optimizer is possible. And finally, we define actuation. What is interesting about these agents is that we define actuation to be both local and global. It is local because the controller can change the resting length of the springs and can thus potentially initiate some form of movement in the robot, if it starts like kind of rolling over itself. Notice that here we're changing the resting length, whereas the actual length of the springs in the simulation depends on the frequency and the damping ratio values of the springs. But we also have global actuation, and the controller can modulate global actuation by changing internal pressure. And this turns out very important because changing internal pressure, as we've seen before, allows the agent to morph and to potentially assume an infinite gamut of shapes. Finally, as far as the experimental setup is concerned, we test a wide array of morphological conditions. In particular, we test 3 different shapes, small, medium, and large, on 2 tasks. So to answer the first question, can we optimize pressure-based soft agents for a given task? We experiment with locomotion on hilly terrain, an instance of which is depicted here. And why hilly terrain? Because if we were to test just on flat terrain, as is usually done in evolution robotics, that would be too easy a task. That is a task that can be easily solved also by periodic controllers, by open loop controllers. On the other side, we had random kills to make adaptation more challenging and to test whether our agents can optimize some minimal form of cognition. And then, for the sake of the second research question, that is, can we effectively exploit shape change for pressure-based agents, we test with an escape from cage task depicted here on the right. So as you can see, the agent is placed at the beginning of the simulation and at the center of a cage. So it is surrounded by kind of 3 different sides by an immovable cage. And its goal is to squeeze through the apertures in the cage. And the apertures are such that it is impossible for the agent to squeeze through them without morphing, without shape changing. Notice that in both cases, fitness function is to maximize the x velocity, which means that in locomotion, it must travel towards the right because it starts off with an immovable wall on the left. And in this case, it can choose whatever direction it wants. And finally, we perform 5 evolutionary runs of 10,000 fitness evaluations each. And what we discover is that indeed, pressure-based soft agents can locomote on hilly terrain, as we can see from this video of a funny virtual creature walking. So as you can see, the strategy it comes up with is basically to roll over its envelope. It shortens the springs on the front and stretches those at the bottom. And we also find the behaviors to be really lifelike. So here, I mean, as you can see, this working behavior kind of looks like the working behavior of unicellular organisms. It even seems to protrude the front part of its body to grasp the terrain in front of itself. And we even performed some ablation experiments to test whether both actuation components, local and global, are indeed necessary for locomotion. So here we plot on the left a treatment with pressure control, that is everything we've seen so far, against a treatment without pressure control on the right, where there is only local actuation, so the controller can just change the resting length of the springs for the 3 different shapes. And we plot in terms of the velocity on the y-axis against the number of fitness evaluations. Intuitively, we want velocity to be maximized. And what we see is that the treatment with pressure control does indeed outperform the one without pressure control, at least in 2 different shapes, telling us that controlling pressure is indeed necessary for achieving effective behavior. And we also tested ablating the local actuation component, that is, the agent can only change the global pressure, but this resulted in abysmal performance and don't even report the results. So to conclude, both actuation components are necessary for locomotion. But there is more.
2 minutes, please.
Yeah.
Yep.
Pressure-based soft agents can also escape from a cage. As you can see here, it's really decreasing pressure. It is flattening on the ground to squeeze through the aperture. And the behaviors are also very lifelike, I would say. They really look like kind of the amazing squeezing feats of the cephalopods. And even for this, also for this task, we tested whether both actuation components are necessary using the exact same setup as before. And what we can see is that the treatment with pressure control greatly outperforms the one without pressure control with all 3 shapes. And the ablating local actuation also this time resulted in abysmal performance. So to conclude, both actuation components are necessary also for the escape task. And to conclude, we envision many exciting applications in the future, like the modeling of soft robots. Indeed, many existing soft robots do rely on pressure, like for example, using pumps here on the left or using inflatable tubes, as we can see on the right, as well as many exciting life applications like the modeling of biological cells. The code is open source if you'd like to play with that, and I thank you for your attention.
Thank you very much for this fascinating talk. I would have one question. You said you have a gas model. Is it inside of the connections of these nodes, or is it inside of the circle that is formed?
Okay, so basically,
where is the gas?
Yeah, so basically it is, the gas is inside of the envelope. So it's basically like a balloon. So the balloon, yeah, like the envelope.
Like the red one that we see here, similar,
Yeah,
sort of.
Yeah, exactly. And in the simulation, so that is modeled by exerting pressure on the masses. So the rigid bodies, the red squares. You model pressure as a force that pushes from the inside towards the outside.
And is there sort of conservation of mass for that gas, or is it always the same in the whole body, or does it need to excrete gas and then suck it in again when it needs more? Is it, or is it a closed system, the overall gas in the whole organism?
It's the second one. Yeah.
So it's an open system.
Yeah, it's an open system.
Okay, thank you. Do we have questions in the chat? Okay, so I had some reminders on, do you know Frei Otto, the architect, who had this concept of the pneu? And then he was doing like all his architecture around those minimum energy structures, like the Olympia Park in Munich, for example, is like one of the most famous pieces.
Yeah, I think, I mean, I'm not really into architecture. I think I've heard of him, Frei Otto, yeah.
Yeah, so he brought that into architecture, like, I don't know when, like 80 years ago or so, but not for moving, but for buildings that don't know. I think they can even change, but very slowly.
Thanks for the pointer.
Okay, any more questions? So that microorganism that we were seeing as a comparison, was it also walking over a landscape, or was it seen from above?
Yeah, it was walking over landscape. So you're referring to Trichoplax, right?
Yeah.
Yeah. So yeah, Trichoplax. I mean, I brought it one because it's an interesting example. In that case, it was actually, here it is. It's actually, I mean, it's a wonderful example because it's Trichoplax locomotes by self-organizing its cilia. So it has like a whole array of cilia. It can actually self-organize to produce locomotion and the hunting behavior and so on. Yeah.
But in the simulation there is this ground terrain below, and then the organism is crawling. And are we also seeing the organism from the side crawling over, or do we see it from on top?
Oh yeah, I got it. Yeah, this one is from the side actually. So this is the ground.
Yeah, and the real organism also has
the other
seen from the side.
It's from above, yeah.
Okay, so thank you.
Thank you.
And we prepare the next presentation. I think Markus Krellner is now here.
Yes.
Are you going to present?
Yeah.
Yeah, okay. You made me nervous a bit.
Sorry, I had to be somewhere else, but I tried.
Yeah, everything okay. I was just wondering what we do with that slot. So can you start your screen sharing?
Sure. So I think, wait a sec. Yeah. That's the one, right?
It's still black on my side, but it says it's going to start something. Now we see it.
All right.
It
I hope
says
my
slide
internet
2.
connection is good enough. Yeah.
It says slide 2. So is this the start?
Oh yeah. Sorry.
Okay. Okay. So thank you. So next up is Markus Krellner and Dian Han with the very pronounced title, "The Last One Standing." I'm very curious.
All right, thank you very much. Yeah, it's basically you will probably understand the joke at the end. And I will give you an introduction and an overview of recent developments in game theory, evolutionary game theory, on the topic of indirect reciprocity, and more particularly indirect reciprocity and the private assessment. And what it all means probably will be explained shortly. So to start off with indirect reciprocity, basically imagine we have a population that's very large. We have only random interactions between people. Maybe they never see each other again. And we still would like them to be helpful to each other, right? Like, for example, if B is like starving, we would like A to share some food with him when he has abundant food resources. But as many of you might be familiar that there's this problem, like if you are selfless, if you are altruistic, they actually can hurt your evolutionary survivability. So what we want to do is like indirect reciprocity is like when you help B, you should eventually get help from somebody else that is not B. That's why it's indirect. And to achieve that, we have to have some intermediate steps. And the first of one is that others need to observe your action towards B. And they will basically assess your behavior and they form an opinion about you. Like when you are helpful, probably they will say, yeah, you're a good person. And because you're a good person in their mind, they will then choose to help you in return. And that's basically the idea. But of course, there can be a lot of complicated things, a lot of problems with it. And what we will focus on is the different sorts of assessment rules you can create to deal with these problems. Much of the research has assumed that the action is quite simple and also the actual reputation. You can be either good or bad, and that corresponds to you get help or you don't get help. But assessment can be much more diverse, so to say. And to give you a classification of all the different strategies, I use this metrics, where you basically say, okay, I need to assess cooperation and I need to assess defection. And I can either don't like it, which is the minus, or I can like it, or I can just not care about it. So if I like it, I will increase your reputation if you do it. If I don't like it, I decrease it. And if I don't care, I just leave it as it is. And I cannot only judge you by your actions, I also have to, or supposedly I have to include what is the person that you are interacting with. And is it a good person or is it a bad person? That's why I have two matrices. And then more complicated still, we can have the situation where it's not a general rule, but it depends what state you're already in. So if you're good, you will be bad afterwards. And if you're bad, you will be good afterwards. And you kind of flip the whole thing around. And this is this fourth value here. And with these two matrices with 4 by 4 each, we can describe basically the most important strategies that were studied in this field. And they are so-called leading 8 because there are 8 of them. And they all have in common that cooperation towards somebody good is considered good, and defecting towards somebody good is considered bad. So that's a space they all share. But when you meet somebody bad, there are very different rules you can apply that actually work in these cases. And what you basically see is that they form this rectangle here, and they avoid just two things. They avoid assessing defection as bad, especially if it's a good person doing it. This is the top row. When a good person is doing it, it would be assessed bad. And the bottom row, it's evil person would be assessed bad. So that's what they avoid. And this was back then when we considered public assessment. And public assessment means there's a population, and the population has only one opinion about a certain person. All agree on this person being good or bad. But of course, that's not a very interesting or a very realistic scenario. So we make it more complicated. We give now each person an opinion about each other person. And then you can have really like messed up matrices, like some agree, some don't, some more randomness in the whole thing, more complexity. And what I want to show you is that new approaches that try to predict what's going on in the spiral assessment situations, and what we basically try to learn by combining their results. So first of all, there was studies that said, okay, if we have private assessment, we basically almost have no cooperative strategies left. They are not stable or they're not cooperative anymore. And basically, these are the three ones that kind of survived this first testing. But these models basically considered rare mutations, which is a simplification that's used for mathematical analysis. And when you have a bigger space where you can have different selection strength that basically determines how much your payoff difference to other people make you decide, okay, if I want to copy them or not. So you have a high selection, you only copy those who are very successful, and you have a low selection, you sometimes randomly copy other people. And then you have mutations, where basically you introduce new strategy or possibly new strategies without any payoff consideration. And when you have this like this, and you consider what you expect in terms of cooperation, if you have very high mutation and have very low selection, you can just have cooperators being around because there's nothing pushing them out of the population. Like the evolutionary pressure does very little apply, or they're just coming too many back in. So you have high levels of cooperation, even if you don't apply indirect reciprocity at all. And the lower the mutation rate gets, and the higher the selection strength gets, the lower are these percentage of just cooperators, and the defectors take over. And so that's what we kind of see with the previous results. If you have very low mutation rate, you only spend time, or let me start. This is a population space, a simplex, where you can basically have all combinations of 3 different strategies. So you can have 10 of the L1 type, you can have 20 of LC, and you can have 20 of LD, and you would be like in this position, and then you could move around. But when you have low mutation rate, you spend most of your time in the corners, and you move maybe alongside the edges, or maybe move back. And this is a very different dynamic than when we increase the mutation rate, because then we actually see that the population spends time in the intermediate states, and we see that a mixture of a discriminating strategy and an unconditional cooperative strategy is much more stable than the all defection strategy, basically. And this means in the end that we have high levels of cooperation where we thought before that there are no cooperation. And this is the results of the 4 strategies I showed you before. And you can see that 2 of them are quite successful in many spaces of mutation and selection strength. And when we plot it like this, again, in our graph, you can see these are the 2 most successful ones, and we have a few ones that are somewhat successful in this consideration. So now these were all results based on simulations, because this image matrix that I showed you before, where everybody has an opinion about everybody, is very hard to describe. But there are new developments that you have the ability to analytically predict how the reputations will form out, and therefore how the payoffs will be in the end, and therefore how the strategies, which strategies will survive, or which states are reached in this simplex. And you see that although it's not quite the same, because the right one is still deterministic, the left one is probabilistic, you see that the arrows basically explain somewhat why this state is so stable. The further you go to all the faction, the stronger the current towards a discriminating strategy becomes. And so it ends up in this top right corner. And when you apply these this replicator dynamics, and you look for all sorts of possible strategies, not just rehashing the old ones, you still find the old ones again. This are the OA type. Basically, if you remember, this was the leading 8 rectangle, and the middle ones, you find them again to be evolutionary stable and correlative. But you also find another type. And this is has a wider area. And now what seems to appear is that you avoid assessing cooperation towards somebody bad as something bad. You still either like it or you don't care if somebody helps a bad person. And this was actually shown with replicator dynamics, and it was somewhat replicated if you look at evolutionary stable strategies. So we don't look at the whole space of population combinations. You just look, you have an infinitely large population of residents, and you have an invader, and can the resident beat any invader, basically, right? And you find again the original leading 8 strategies, at least those 3 here. And there's one new one. It's kind of probably works a little similar to those, but it's outside what was considered before. But again, you avoid these areas here and these areas here because it does not seem to work.
1 minute.
So when we put it all together, we basically say this strategy here, right? This is always the combination, right? And this strategy here seems to be the best. And this may be a close second. And now you think, okay, why is it the last one standing? Because it actually has been dubbed standing like 20 years ago. So it was one of the first strategies to be proposed as a indirect reciprocity without any mathematical models really backing it up, just saying, okay, this makes sense. And when we now combine all these different research, we find it again. And that was kind of an interesting thing that I wanted to show you. I guess I have to skip that, and also, yeah, maybe one more sentence about different other developments. I just showed you that we have found different new assessment rules, but we also replicated the old ones. But other researchers have found that if you not deterministically say, okay, every time you think it's good, every time you think it's bad, you can actually say 90% of the time I think it's good, but with 10% I think it's bad. You can also have some interesting dynamics and improve things. What I myself did is I introduced a strategy that works before the assessment, where you have the donor, if he has to decide, do I help this guy, is not considering just his own opinion, but also considers the opinion surrounding him and tries to make as many people happy with his action as possible. And although that seems kind of selfish and like opportunistic, this improves cooperation at any cases that we looked. And in just in comparison to that, there's another research that called their mechanism empathy, but this works on the observer side. So the observer sees somebody defecting, they may consider, okay, yeah, this guy is just defecting, not because he's a defector in general, but he has a bad opinion. And so we let it pass, basically. And if my time is done, then yeah, I'm happy to take some questions.
Yeah, unfortunately, we have less than 1 minute time remaining. So if somebody has a very, very short question that looks for a short answer, doesn't seem that way. So thank you. Maybe we can skip the questions and shift them to the chat. Sure. Or on Slack.
I will be in the chat sometime, yeah.
Yeah, okay. Thank you very much. And we come now to the last presentation, which is by Victoria Rajewicz. I think Sylvia should start the video. Yeah, perfect.
My name is Victoria. I'm very happy to be here. I'm a biologist at the University of Graz, and today I'd like to talk about the biohybrid entities for environmental monitoring. So firstly, I have to start with the concept of environmental monitoring, why we need it, and why we even bother with the new approach that I'm going to talk about in a second. So by now, most of you know that the planet Earth is faced with a huge ecological crisis, and the habitats that are the most vulnerable to all of these changes are also the ones that are of major importance to humans, which are the freshwater supplies. So the freshwater supplies are steadily diminishing due to many factors like droughts, agriculture, microplastics, tourism, overpopulation, and many, many others. And so we need the water monitoring to identify any trends and changes, to set protection programs in place, and generally to just gather data on the limited supplies that we have left. And so far, this has been done by traditional monitoring methods, for example, manual water sampling, like taking a sample, transporting it, and analyzing it later on, and classical sensors like oxygen probe, temperature probe, etc. And of course, these monitoring methods work really well because they're very accurate and they're very precise, especially if we're interested in one or two environmental factors. But let's say we want to monitor the environment continuously over really, really long periods of time. And this is especially where water sampling becomes quite suboptimal because it's very time intensive, it's expensive, it's labor intensive because those samples need to be taken, transported, analyzed by qualified staff. And it's also something I call one-off monitoring. So it gives us information on the water quality at the time of sampling, but not necessarily in real time. And this makes the detection of sudden events like oil spills or any toxic spills delayed in time, which is not ideal. But organisms react to it all. So organisms react to the end result of all these complicated factors happening in the environment. And that means that by selecting a species that is a good bioindicator, we can really gain insight into the overall water quality, which will give us a new type of data, which is less precise but more broad. And this is where we introduce a concept of a biohybrid, which here we define as a structure that connects biological entities, for example, living organisms, and synthetic materials like electronics that allow us extracting useful data from those biological entities. So here we have an example of what the biohybrid might look like. The blue parts represent the electronical parts, synthetic materials like cameras, power supplies, etc. And everything else are the life forms that can be either supplied to it or will grow naturally on it, otherwise come to it. So this setup will allow this electronic core to extract data from the life forms that are in close proximity to it. Now, before I go further, I would like to talk about our project, which is working on exactly this biohybrid. We're the project Robustinosis. We are a European Union funded project with a budget of 3 million euros and a runtime of 5 years. Our starting date was in October of 2020. And at the University of Graz, we are the main biological partner and also the coordinator. Also, we have the pleasure of working with our partners in Sant'Anna in Italy, University of Brussels, and Durham University. The core features of the project is, of course, firstly biomonitoring. So we want to monitor the environment by observing the organisms that live in it. Nextly, we've got the autonomy. So we are aiming for extremely long experimental runtimes by supplying the biohybrid with its own autonomous energy source. And lastly, biodegradability. We're aiming for major parts of the setup to be biodegradable. So we're going to be using materials such as wood, compostable plastics, and others. And this is, among others, to reduce the waste that is often produced during research projects. So firstly, what we have to do is we have to choose an organism that is a good bioindicator that we can observe. As much as I would like to talk about all the organisms that we're considering, for the sake of an example, I'm going to start with the water flea or Daphnia, because Daphnia is really the perfect place to start when it comes to bioindicators. It is very globally distributed, it's easy to work with, easy to culture, etc. And it reacts to a lot of different things that happen in the environment. For example, low oxygen, pesticides, changes in temperature and pH, heavy metals, and many, many others. And it has really specific responses to all of those stressors. For example, changes in the swimming pattern, like erratic swimming, changes in phototactic ability, so the reaction to light. Mortality, of course, is a sign of stress, or hemoglobin accumulation. So now that we have chosen our species, what is the optimal way to observe it automatically with this setup? So here is one of the setups that we've built recently for Daphnia observation. Here we have the main robotics tube that contains all the necessary electronics. For example, Raspberry Pi, which is like the control center of this particular setup. And to Raspberry Pi, there is an attached Raspberry Pi camera, and the camera is facing directly this chamber. This is a flow-through chamber, so it has mesh, so the water can flow easily through it. And essentially what it does is trap Daphnia so that the camera can observe it easily. So now I'd like to share some snippets of the footage that we've managed to take with this setup. So here is the view as if we were a human trapped inside a tube. So we're looking at Daphnia. All these little dots are the swimming animals. They're very small to us, but they're enough for a computer. So this is what it would look like normally, and this is what the computer sees after the footage has been analyzed. So now the white elements are the Daphnia swimming around. So this footage was taken in the field. So this was to test the setup and to see how Daphnia behaves normally under normal conditions, so in their natural habitat. And now that we know that this setup works, and it works well for, at least for Daphnia swimming, we still need to calibrate the sensor. So we need to know how Daphnia reacts to which stressors, so that we know how to read its behavior. Starting with swimming behavior is really an umbrella term for a bunch of different behaviors. So first we have spinning, so when Daphnia literally swims in those circles, spinning movements. Then we have movement inhibition, so when Daphnia stops swimming and sinks to the bottom. Then we have the swimming speed, swimming height, swarming, and dial migrations. So all of these are behaviors that we will be taking under consideration. But again, for the sake of an example, and some place to start is the spinning behavior, because it's quite obvious and it's easy to observe, and it's a very clear sign of stress. So here is a comparison between the two swimming trajectories. On the left, we have the normal swimming. So this was taken in the lake. This is in their natural habitat. So we see that normal swimming is presented in this almost semi-straight line, interrupted by these little hops, because this is how Daphnia moves through water. But generally, this is a straight line. And on the right, we have the disruptive swimming. So this was taken in the laboratory after a stressor has been added to water. So we see here that the trajectory is much more curved. This is what we would already classify as spinning, and the angles are much more smooth instead of sharp compared to here. So we compared the two angles of turning, and the chi-square test between those two data sets was significant, which means that Daphnia is much more likely to present those smooth curves when there is a stressor present in the water. As a summary, my take-home message is that by reading the organism's behavior, we can really gain insight into the overall water quality and all the changes that happen to it. The project Robustinosis develops the methodology for a biohybrid for environmental monitoring. And here we define the biohybrid as a structure that connects living organisms and electrical parts. For more details, please visit our website. But for now, thank you for your attention, and I'm happy to take questions.
Yeah, thank you, Victoria. Great talk, great timing.
Thank you.
Do we have questions in the chat? Or just raise your hand and just ask. I think you mentioned something like an energy source during your talk. Could you maybe, in the meanwhile, go a little bit more in detail there?
Yeah, of course. So the main power supply that we're working on right now are microbial fuel cells. So it's a fuel cells that, well, uses microbes as an energy source. So essentially what it is, it's a device that you can dig in mud, and essentially it draws electricity from the respiration of the bacteria present in the sediment. So for more details about this, I probably consult more the engineers that are working in our team rather than myself, because I'm not working on it personally. But it's in a development stage right now.
So the more organic matter you have on the ground, the better it works, sort of thing?
Sort of, yes. Yes, I think so. So this would be a really good solution to really long run times, because assuming this would really constantly be happening in the sediment, those processes, and then the energy can be stored and reused.
Okay. Any more questions? So these stressors that you were talking about, so what meant pH changes, I guess, temperature. So can you expand maybe a little bit on that?
Yes, so there's a lot of different stressors that I am really looking forward to testing. For very first lab trials, I was using salt, which is kind of the most approachable one to work with because it's the easiest one and there's no harm done pretty much. Because the ones that I would really like to explore sometime soon are, for example, heavy metals or drugs. I mean, drugs like paracetamol. But this is, let's say, later stage. And for the first test, salt was really the easiest one to start with. So for now, I'm working with this. I think later on, I will move on to raising the temperature, which is a little bit more applicable to the actual stressor that can happen in the lake, and pH for sure as well.
Okay, so the last talk was about the last one standing, and the finish of this talk is about drugs and heavy metal. So how else could we finish that session now? Thank you, Victoria.
Thank you.
And I think the next session starts immediately. Oh, I just saw there is a question of James. I think we still have 2 minutes. So James, would you like to? No, I will probably read it. How consistent are the results likely to be over time? What if the species adapt to the changes in the environment, Victoria?
So I would say they're likely to adapt to it over time, but what we're actually going for is to notice when the change happens. So if they adapt to it, let's say after a couple of weeks or something, that's still okay. But what we were going for is the precise moment when the change happens. And then, for example, something happens, a toxin leaks in a lake, and all the Daphnia starts spinning. So either we either adapt to it or die, but essentially the change will be likely to be detected with this behavior.
Okay, adapt to it or die is also like good final words. Thank you, Victoria.
On this positive note,
Yeah.
I take my leave.
Okay, thank you.
Thank you.
So let's carry on with the next session. Unfortunately, I don't know who is the next chair. maybe
It's
Silvia.
me. Hey,
Yeah,
it's
okay.
me, Wolfgang.
Hi,
Hi,
Wolfgang.
hi, Thomas, and welcome all to the next session, which starts right now in a minute. And Sylvia promised to start the first talk, which is a video on YouTube. Sylvia, do you want to say?
Yes, I'm doing it now. Yeah.
Hello, I'm Du Mai Nguyen from Computer Science at the University of Colorado Boulder, and our paper today is Physical Obstacles, Constraint, Behavioral Parameter Space of Successful Localization in Honeybee Swarms. So in our work, we focus on the honeybees, which often have been a model complex system. And these are systems with two broad characteristics. They self-organize without central control, and the interactions and communication between relatively simple individuals can give rise to patterns with emergent properties that we see at the collective behavior level. And a colony typically consists of thousands of fertile male drones, one fertile queen, and tens of thousands of sterile female workers. And the queen is attended by some workers so she can perform her role as a reproductive machine and a regulating factor for hive cohesion as well as for reproductive swarms. And these are the swarms that happen when a lot of the bee population leave with the queen and try to create a new colony. They focus on, and we focus on our research, on these swarms. While there's a lot of knowledge about the house hunting process after they form the swarm, and we also know that the queen's pheromone regulates swarm cohesion. One aspect that's not been fully explored yet is how they can find the queen to form the swarm in the first place, and also in the presence of a lot of environmental perturbations. So I will talk about some of our earlier findings in a little bit. Another relevant piece of background for our work is pheromone or chemical communication in the bees. Bees of all types, brood, workers, queens and drones, exchange these chemical signals or messages. These signals are emitted by the bees' bodies, diluted and carried by air currents, and are received by their antenna. And the worker bees are the main workforce to maintain a colony, so there are a lot of different pheromones involved. One of the most well-known and readily observable signalings is the pheromone secretion from the Nasonov gland. So a worker bee would point up her abdomen and open up this white gland to secrete the chemicals. And she would also fan her wings to disperse the chemicals that decay rapidly in time and space. And it's a behavior called scenting, which is central to our work on swarming. So going into the previous works that lay the foundations for this paper, this is our experimental setup where the bees are in a semi-2D arena, so restricting them to only walking and no flying for easier handling and analysis. And there's a light board underneath to make a clean recording. And the bees are searching for the queen who's in a cage, and we record the behavior from an aerial view over time. We collected a lot of video data of bees in a semi-2D arena, so to extract the data from these videos, we use a mix of classical computer vision methods and machine learning, specifically deep learning, to detect bees and recognize the scenting behavior. So to focus on the deep learning methods for sake of time, we built custom training data sets for convolutional neural network or CNN models. So for a given bee in an image, we label it as scenting or non-scenting based on the wing angle. And we trained a binary image classifier which achieved about 95% accuracy. We also label the head and tail to estimate the scenting direction. So this is a CNN regression model that achieved about 96% accuracy within a 15-degree error tolerance. And as a result, we can automatically detect scenting bees in the videos. So here's an example where the queen is in a cage and worker bees were placed far from her, and scenting bees are shown as blue arrows pointing in the direction that they scent toward, which is behind them. And over time, they scent a lot in this communication network and then eventually swarm around the queen. So using that data, we want to correlate the scenting directions with the localization and aggregation of the bees. And we take the position of a scenting bee and its scenting direction and treat them as a set of gradients that define a heat map or an attractive surface with some height f. And high values of this function tell us the locations where the pheromones may be higher and the bees may be more attracted to. So here's a video of the same experiment on the right side. We also show the attractive surface reconstruction over time. And as more bees are finding the queen, the yellower region of higher F values tend to be where the queen is and where the bees eventually aggregate. And these are the main findings in a recent paper titled Flow-Mediated Olfactory Communication in Honeybee Swarms. So next is another previous paper, an experimental paper testing the robustness of collective scenting in the presence of physical obstacles. And this is the main work that inspired the modeling paper that we submitted to ALife. Through the work in the first paper, we have tools and machine learning models that we can leverage for the remaining paper. And in these experiments, we compare two main scenarios. No obstacle and a linear obstacle or a bar in the middle there. So without an obstacle, many bees begin to scent right away and make their ways to the queen. And on the other hand, with the linear obstacle, they are stuck behind the bar for some time until they can explore and find the opening or the escape point. And the quantifiable temporal properties support these observations. So in blue, or the control experiment with simple environment, the number of scenting bees peak early on, and there is a quick drop in the distance to the queen without the obstacle. And in the linear obstacle in green, a lot of scenting occurs early on behind a bar, around 900 seconds or so, when there is a smaller peak in scenting, and as they find the opening and scent towards the queen. And the distance to the queen also reflects that, with a relatively constant distance until they begin escaping. So these experimental results show us that physical obstacles lead to a temporal delay in the scenting network formation and also the aggregation. So to explore further how physical obstacles can affect the behavioral parameter space of collective scenting, we turn to modeling, which is the main focus of our ALife paper. So the model is an agent-based model that has some main components. We model pheromone flow and decay with the diffusion equation, which tells us the concentration C of a substance at a given time and position. So we provide values to these parameters of the equation: the initial concentration, the magnitude of the directional bias, or WB, the diffusion coefficient, the vector for the emission direction, and the decay constant. And in particular, the WB highlighted in red is one potential behavioral parameter adjustable by the bees, and it mimics the bees fanning behavior to direct pheromones behind it. And you can see the difference between an isotropic diffusion, or when WB is 0, versus a directed diffusion process when WB is higher than 0. And This is also one of the main reasons why we use modeling. The model allows us to compare these kind of signaling strategies in the collective system. Since in the experiments we're limited in, for example, cannot ask the bees to turn off the fanning so that we can have a better understanding of how the parameter values can impact the collective pattern that emerges. So another big component of the model is how the bees behave in this virtual space. So we created bees that follow simple local rules. So if you're a bee, then you start out by walking randomly, and then when a pheromone concentration threshold T is met, then you have a 50-50% chance of scenting or walking up the gradient as shown here. So in our model, we focus on varying these two behavioral parameters, WB and T. And before implementing any obstacle in the model, we tested a fairly simple environment without any perturbations. And this is the work also published in the same PNAS paper that I mentioned before. So we let the virtual bees live in the 2D space, and we created these phase diagrams based on those two parameters, WB and T. And what we observe is 4 phases that happen. And to clarify, we don't, by phase, we don't mean a moment in time, but more the overall dynamics and eventual outcome. So when the threshold is too high, no bees are ever activated to scent, so they just walk around. And on the other hand, if the threshold is too low combined with a lower WB or directional bias, then most of the bees are scenting, and they would quickly form these small clusters or local equilibria. And at the intermediate values of the two parameters, one thing that we see is a sort of diffusion limited aggregation, or DLA, where the bees can still find the queen, but only when they're very close to her by random chance or random walk process. And then what we would call the most successful phase, where there's relatively higher WB or bias, and before the threshold is too high, then the bees propagate the signals in a sort of percolation network and form a single compact swarm by the end. So I'll skip to that. And overall, the model shows that directional signaling is beneficial to this aggregation process, as we, in WB of 0, we never observed this kind of successful phase. So we took the previous basic model and changed and made some modifications for the problem of observing what happens to the collective scenting network and the aggregation process when there is physical obstacle. So one main change is to adjust the movement of the bees to not occupy the obstacle or be able to jump over it. Then we also need a way to model the pheromone diffusion to reflect the fact that pheromone can't flow past the obstacle. And the way we do that is by a relatively simple line of sight method. Here the line CD makes up the wall, and then line EF is the line of sight from a scenting source, or bee, to a pixel in the discrete grid. And we write the linear equations for these lines and check if the lines intersect. In other words, if there is a solution. So if the lines intersect, then the pixel will not receive the pheromone from this bee. So for a scenting bee, we have a sort of Boolean mask array that says what pixels should have pheromone from this bee. And here, as an example, the area that's grayed out, it represents the area that would be 0. So with the changes to the model, we can run simulations like this, where again you can see some of the propagation process, and then them trying to swarm at the end. And we search over the range of parameters for the WB, or emission bias, and the threshold, or T, that we previously tested before. And we ran simulations for environments with and without the obstacle. And in both, we see the similar 4 phases of outcomes, where there are small clusters, or clusters mostly via the random walk, and scenting bees that are, if there are any, they're very close to the queen. the successful phase of clustering via the percolation or propagating the signals. And here the obstacle leads to a temporal delay in scenting and aggregation, as we saw in the experiment. So 900 versus 5,000 time steps to see a network forming. And finally, no clustering when the threshold is too high to trigger activation of scenting. So comparing the time series of the phase 3 simulations, we see that the temporal delay in the average distance to the queen, the queen's cluster size, as well as the number of scenting bees and the farthest distance to that scenting signals can spread to. And one of our main purposes of modeling is to see how the behavioral parameter space is affected by the obstacle. So we constructed the phase diagrams for those two conditions. And again, we see all phases present, as I show in the last slide, but the boundaries have shifted for phase 1 to 3. The successful percolation or aggregation of phase 3, or the pink blocks, also occupy a smaller area of the diagram when there is an obstacle. So to quantify those pink areas, they are 33% versus about 12%. With low values of the threshold, most of the area that is phase 3 here becomes phase 1 when there's an obstacle. So the physical wall leads to the breaking of the chains of scenting bees in the network. And there are smaller clusters that form on both sides of the wall. The phase 3 region with higher values of T becomes phase 2 with the obstacle, as the wall separates bees from one another and prevents a scenting network from forming. And in our first paper, without obstacles, we previously show how as the bee density increases from 50 to 100 to 300, this region of phase 3 also increases as there are more bees to create and sustain the network. So in this study with testing obstacles effect, the shrinking of the phase 3 due to the obstacle suggests that the wall may have a similar effect to decreasing the total density. In other words, the obstacle decreases that effective density of scenting bees available. And potential future direction would be to test different densities with the obstacle, and to answer the question of, is there a critical density below which the phase 3 will disappear completely? So the main takeaways of this paper, one is physical obstacle delays the scenting network formation and the eventual aggregation around the queen. But the bees can ultimately overcome the challenge and achieve the collective goal until it hits some limit. And through modeling, we see that the behavioral parameter space is more constrained as a result of the spatial heterogeneity in the bees. And additional potential future directions can pursue testing different obstacle lengths, apertures, and placements. And also, since physical obstacles are not the only environmental perturbations that the bees encounter, there are other perturbations we can test, like wind, or if the queen was a moving queen, a moving target instead, and along that line. And finally, thank you to my collaborators for the overall work as well as for this specific paper. So my advisor, Dr. Uri Paleg, Michael Gonar from CU Boulder, and also Dr. Greg Steffens and Dr. Keisha Bozek for helping with the machine learning development, and also my lab for very useful feedback, and the school and also the NSF funding source. Thank you for your time.
Thank you, Jill, for this talk, which was very interesting. And for people that are not in bee research, it was very well explained, I think. Is any of the contributors to this paper here? If not, then I would like to ask people who have questions to send them directly to the authors of the paper. I certainly have a question about the assumption of 2D modeling validity for bees, but I will pose those questions either on the Slack if they participate or to them directly. You should be able to find them. Okay, so then I think we should move on to the next speaker. And the next presentation, again, is a 20-minute time slot, is Eduardo Izquierdo, Gabriel Severino, and Haley Merritt, Perpetual Crosses Without Sensory Delay, Revisiting the Perceptual Crossing Simulation Studies.
Great, thank you. Can you hear me all right?
Yes.
Great. Hi, everyone. Really happy to be here. I'm going to be telling you about work that we've been doing in our lab to replicate some really fascinating studies on social cognition. And this is all work in collaboration with two graduate students, Gabriel Severino and Haley Merritt. So I'll start with a broader motivation for this work. The majority of research on social cognition has tended to focus on the cognitive properties of the individual engaged in social interaction. However, increasingly, there has been a push to study the dynamics of the social interaction itself. This is a move away from methodological individualism and towards an interactionist perspective. Crucially, making this move has not entailed making the studies more complicated. On the contrary, some of the studies that have emerged have been rather minimalistic. And partly because of this push towards minimalistic experiments, there has been a strong contribution from computational modeling over the last decade. And importantly, this is an area where experiments have informed the computational models, and insights from the detailed analysis of the models have driven new experiments and in general created a lively experiment theory modeling cycle. One important framework that has emerged in this field has been the perceptual crossing experiments. In this framework, there are two participants that can move in 1D, in a one-dimensional space, facing each other. Each participant has a single binary sensor that they can move around along that one-dimensional space. And as they move around the sensor, they can sense one of three objects. They can either sense the position of the other agent, they can sense the shadow, a shadow of the position of the agent, so an object that just moves at a fixed distance from the agent, or they can sense a fixed object in the environment, in this sort of circular arena of a one-dimensional space. And so again, to be clear, the participants cannot see each other. They're in different rooms and so on. They can only perceive through this simplified binary sensor. Crucially, as they scan back and forth in this one-dimensional environment, all three objects will look exactly the same. So shadow, agent, and fixed object all look exactly the same. So they can't tell what they are by just looking at it or sensing it. They have to interact with these objects to be able to distinguish them. So the goal for the participants is to find the other participant. That's a goal that's given to them, to distinguish the participant from the other objects, and both participants have the same goal. This is a task that humans do very well at, and that has been studied in a fair amount of detail, and I will not be going into those studies here. But so there, again, there's been a number of computational models that have replicated these experiments, and they've done this through the use of embodied neural network models in an evolutionary robotics style. The idea here has been, again, there's a recreation of a one-dimensional environment. In this case, it's a ring, so it wraps around. There are two agents that are facing each other. The two agents interact in this space through that one sensor that each agent has. So this sensor is feeding onto a neural network, a recurrent dynamical neural network, that then, for which two of the neurons in that network are connected to the left and right motor neurons, which allow the sensor to move in that space. So there's similarly a shadow and a fixed object in the environment. The two agents are controlled by different neural networks, but with identical parameters. So they have different states, but the same parameters. And so one agent is rotated in relation to the other one. And so one could, in principle, design a neural network or any kind of control system to solve this task. But the real interest from the computational modeling work has been to employ the artificial life philosophy of establishing only the higher level characteristics of the behavior and letting evolution explore and come up with ways to solve this task, with different ways of solving this task, perhaps counterintuitive ways of solving this task. And in this case, the task is, again, to identify mutual interactions. So finally, here's a specific motivation for this work. As far as we could tell, all of the simulation studies that have worked on this phenomena have reported that a temporary delay on the sensor is necessary for the problem to be solved. And this makes sense, why a temporary delay could be an important part of a successful strategy. Once an agent crosses another agent, if the signal to that is delayed, then they have to always cross, and it's only the two agents that end up doing this, and so they end up in this sort of coordination pattern. And so in all previous studies, they built in a temporary delay, and all of the circuits and everything that has been analyzed in that work has included that. However, from reading the papers, we could know, and this again, this is things the graduate students brought up, it wasn't easy to understand why the experiments without the sensory delay had failed, or in what ways they had failed. They were mostly reporting that they had failed and that they had to add it. And so our initial goal for this study was simply to better understand the failure. Right, so we set out to replicate the experiment as closely as possible in all respects. As far as we're aware, we only introduced the following differences. Again, so we replicated the environment and the agent and the controller and the way the sensory informs the neural network and how it controls the left and right movement. We, of course, varied, in addition to trying the with temporal delay, we'd also tried a version without temporal delay. They tended to use larger neural circuits with 5 and 10 neurons. We only used 2, 3, and 4 neurons, so smaller circuits. And I have to explain a little bit about the fitness evaluation. Typically, again, so the environment is a one-dimensional rings of 600 units of space, which you see here on the y-axis. And agents start anywhere on that space. And then as time proceeds, they move around in that environment, left or right, and then eventually they can find each other or not find each other. And you can see the other lines there are the fixed objects and sometimes the shadows and so on. The fitness was the average distance, to try to minimize the average distance between the two agents over time. The only modifications that we made to this through many different trials, as agents started in many different positions, the only differences that we made were we eliminated the initial transients. We still evaluated an agent by doing the average distance, but only at the very end, in the last half of the trial. We let the agents move freely at the beginning to not force them to have to find each other too quickly. And we eliminated any kind of stochasticity. So the agents in our simulations always started from the same place, whereas in their case, they randomized that. And we use different evolution algorithms, but we don't think that played a role. All right, so I'm going to talk about the results in 3 parts. The first part was, the motivating question was quite simple. It was, can we just replicate their results as they are, temporary delay and everything. We needed this as a baseline before we could modify and extend the experiments in any way. We performed 100 independent evolutionary runs for each circuit, size 2, 3, and 4. Here we show the final fitness of the best individual in each population for each of those runs, for each of the 3 conditions. And so, although we found solutions in all of the conditions, successful ones, so 1 means a good fitness, and the lower the fitness, the worse the agent performed. We found solutions in all of them. It's the larger circuits did better, and in general, as you can tell, most of the circuits actually got stuck around a fitness of 0.92. So we looked a little bit more closely into this. We grabbed agents in the 4 neuron population, and we saw examples of the ones that got stuck in the 0.92 performance and ones that perform almost perfectly. And during fitness, the agents only saw a few trials, perhaps 10 different trials or so on. Here we tested them in hundreds and thousands of trials with many different starting conditions. And we noticed that the challenge to being able to mutually identify the other agent came in the form of blocks of the starting conditions, places where the 2 agents would start where they would not be able to find each other, and other areas where they would. So this means they had cheating strategies for most places to identify each other, but they couldn't truly identify each other because they got stuck in weird places. And so all of these agents would look more or less like this. The block would change space. But then the really good agents, when we tested them more robustly and we moved other kinds of things around, like where the shadow was and velocities and other things to really test for generalization, they would find the agent almost everywhere. And in fact, the yellow and things that you see here is not all white because it takes, this just means that it took a little bit longer for these 2 agents to find each other versus these ones who found each other pretty quickly. And here you see an example run from just one trajectory in this point, where you see the agent in this yellow, the blue in this, the other agent in this blue, the shadows in green and red, and the fixed objects. And then, you know, how they start interacting in the end. And most of these runs end up looking like this. The first question that we wanted to ask then was, of the successful runs, how many of them generalized well? So again, when we do this, so the fitness is a score that's done with just a few runs. This generalization that I showed earlier, is a more exhaustive form of the performance that includes variations and so on. So we tested the best performing agents across the 2, 3, and 4 neurons shown in these colors across this wider range. And actually all of them performed quite well. They were all, almost all of them were robust, except for a few that dropped performance. But the other thing that we wanted to ask was, again, we modified the fitness function by removing the transients. And we wanted to see how much that affected the performance. So here we're comparing the current fitness evaluation without the transients on the y-axis versus the original fitness function that they used in all of those original studies with that included the transients. And what we observed was that there were a whole bunch of agents that were performing almost perfectly, but in the original fitness function, they were being rated as not so good. So it will be all of these ones, simply because in some ways they were taking a little longer to find the other agents, nevertheless reliably finding them. And so I think that may have been part of the problem that previous studies may have been running into. And so, okay, so one more thing that we wanted to look at, another question that we had was, were all of these strategies the same? We had a lot of successful strategies. Were all of them the same, or was there a lot of diversity in the behaviors? Particularly because they only, in the previous studies, they only analyzed 1 out of hundreds of runs that they did. And they all described them as perpetually crossing, always crossing. But when we looked at the number of times these different solutions crossed, we found that a handful of them crossed a few times, but then stopped crossing, just sort of more or less either moved, bounced like this off of each other, or indeed just stayed near each other. And so we found this diversity that had not been discussed before. And so the second question in part 2 was, this led us to the new question, which was the original question. Why is it that agents cannot evolve without that sensory delay? Again, all of those ones had the sensory delay, just as in the original studies. Why was it that they could not? And so again, we set out to perform the same set of experiments. Again, now the only difference was we removed completely that sensory delay. And to our surprise, we again ran 100 evolutionary runs for 2, 3, and 4 neurons, and we actually found that we found solutions even easier than when we had the sensory delay. Again, this is surprising. And the only main change that we think it's there is that those changes to the fitness function. Again, the larger the circuit, the more likely they were to evolve. But we found solutions even in 2 neuron circuits, successful solutions. We asked the same kind of questions, the same kind of analysis to do with generalization. Again, all of those agents that had a good fitness actually solved the task across changes in the shadow, distance, change, many different starting conditions, and so on. But of course, the interesting, when we asked about how many times they crossed each other, it turned out that none of them, almost none of them, actually, there was just one. The majority of these solutions all solved the task in this sort of minimal crossing way, which had never been discussed. So both the human experiments and the original studies almost always talk about the perpetual crossing. But when we removed the temporal delay, almost all of the strategies were very different. And so it doesn't mean that this strategy is invalid, but we wanted to see for our third and last set of experiments whether we could try to get the same kind of behavior that had been observed in humans and in previous studies, still without the sensory delay. So could we promote this sort of perpetual crossing not by introducing a temporal delay, which again is not typically how it's done in artificial life, but by changing the constraints of the task. And so we again set up a new batch of experiments. In addition to removing the sensory delay, the only change was we now promoted crossing as part of the fitness evaluation. So the change was as basic as, first and foremost, find the other agent. But once you find it, maximize the number of times that you cross back and forth with that other agent, so that to make sure to remain close and so on. Solutions. So this did make it hard for the agents without sensory delay. It seems much harder than with them. But nevertheless, we found some solutions. We found 6 in the 3. We found no 2 neuron solutions, but we found 3 neurons, 6 3 neuron and 6 4 neuron solutions, and they were again robust and generalized. And as expected, they all crossed a high number of times. And of course, the original reason we got into this was to try to understand it a little bit better. We haven't gotten to that part of it in as much detail, but I'll give you one example of a successful 3 neuron circuit without temporal delay that crosses perpetually, like in the original studies. Again, you can see its performance across the more general conditions. It almost always finds agents very reliably. You can see many different traces of the one agent in blue and the other agent in yellow. This is a little bit hard to read. And you can see here in the middle figure, one single trace where you got one fixed object. And the cool thing about this trace is that you can see examples of interactions with, you can see how the agent begins to interact with a fixed object, and it tries, what you see here is the neural activity at the bottom, and here the physical space. You can see them interacting, trying to engage it, trying to engage first the fixed object, then the shadow, and then finally engaging with the other agent. And we've begun to look at the dynamical systems analysis, but I will not get into that now. That's work that is ongoing. We have some initial ideas about how this works, but that's the future work. So as a summary, we've successfully replicated the original studies. We've only added a very minor modification to the fitness evaluation and found that temporal delay was not necessary, contrary to a few original works. And have been finding a wider range of behavioral strategies that had not been discussed previously, either in human experiments or in the simulation studies. The next step is to actually analyze not just one, but an ensemble of these solutions using dynamical systems theory. And all of the code is available online. So if you want to take part in this, please feel free to do so. All right, thank you so much.
Thank you, Eduardo. Well done. Extremely complicated system. With, it first looked this is a trivial task, but but then you showed how complex it can become. That's a very interesting thing. Well, I think we do have maybe 1 or 2 questions we could allow because we are already over time.
Oh, sorry, okay.
Seth Bullock has a question in the chat.
Yeah, my question might not make sense, Eduardo, because right at the end, did you say that with human participants, they also do not need temporal delay, or do they need temporal delay?
Sorry, 1 second. I started sharing. I shouldn't have. To be honest, that's a tricky question. I think one of the arguments that Ezekiel makes is that there are just temporal delays. No, they don't build in temporal delays into the sensors and the apparatus. But there might be an inherent temporal delay in the whole thing. But for me, there's a theoretical question of, is a temporal delay necessary? I understand that there's a technical temporal delay, but I don't think that it's necessary
human participants never develop the strategy of oscillating close to, but not crossing the other agent. Is that true? They always cross.
To be honest, I talked to Ezekiel for a little bit. I think they have seen strategies where the agents cross a few times, 4 or 5 times, and then stop crossing. I think that might be a more natural strategy for the human than
perpetual crossing.
Than the perpetual one. So actually, I think the resting after a while it might be more common.
So your simulation results actually align with human results reasonably, we think.
I think I might need to check and speak to these people who are running these experiments more to really say that, but I need to have those conversations.
Great, thanks. But really nice talk.
Thank you, Seth.
Thank you very much. Is there anyone else? I wanted to allow 2 questions. This was 1. Anyone else?
I guess I'll read. There's one. Anselmo says, how can one distinguish the avatar from the shadow? Again, the way they designed this in a very clever way, you cannot, by just, again, it would be as if saying, by just scanning over them, you cannot. The shadow looks exactly the same as the individual. The only way in which it will be different is that I start moving back and forth, and I sense that you're moving back and forth, or something like that. I have actually not done the human experiment. I should do it. I should join, but it's just it's like a dance. The only way to distinguish it is you're sensing that there's a human back there,
which is difficult in a one-dimensional.
Absolutely. And in fact, people spend, if you look at the human experiments, people spend a fair amount of time on the shadow and on the fixed object. So they're really like going back and forth and trying to figure it out. So it's not trivial. Yes.
Yeah. Okay. Right. Thanks very much, Eduardo. Do the experiment yourself.
Yes, I need to. Yes. I need to. Yes. Right. Thank you.
Okay. Perfect. Our next speaker is Chantal Nguyen, who is giving a presentation together for work with Isabella Huang and Orit Pelek, Firefly-inspired vocabulary generator for communication in multi-agent systems.
Thank you very much. So hi, everyone. I'm Chantal Nguyen from the University of Colorado Boulder. And today I'll be, as mentioned, talking about a Firefly-inspired vocabulary generator for communication in multi-agent systems. So this work is inspired and motivated by fireflies, which on a warm summer's night, put on these dazzling light displays like the one you see in the background image here, which serve as massive mating rituals. So fireflies have a lantern organ in their abdomen, which can produce bioluminescence. And many firefly species produce light in order to search for, attract, and communicate with potential mates. Some firefly species produce light in the form of a steady glow, while others will produce light as a series of discrete flashes. And we're particularly interested in those species which produce these series of flashes as they can potentially encode information. Male fireflies in a swarm are typically airborne, and they'll flash according to a species-specific pattern, an example of which is shown here, consisting of a few flashes in succession, followed by a longer pause, to attract and locate females, which are typically on the ground or in the brush. And in this pause in the male pattern, the females can flash in response with a species-specific delay. And the female responses tend to be relatively less complex than the male flash patterns. So we're here in this work, we're focusing primarily on the male patterns. Two fireflies can flash back and forth at one another until they locate each other, make contact, and potentially mate. But multiple firefly species can and do overlap in the same habitat, leading to instances of misidentification and failed interactions. So how can fireflies correctly identify potential mates of their own species in the presence of potentially much visual clutter caused by fireflies scattered throughout some area, flashing at different places and at different times, and potentially according to different patterns? This presents something akin to the cocktail party problem for the fireflies. So the cocktail party problem is when you're in a crowded party, how do you filter out all of the background noise and chatter and music in order to focus on the conversation that you're having at hand? One partial way to alleviate this cocktail party problem for some firefly species is in synchronization. So when the males synchronize their flash signals, this presents a unified signal to the females and also synchronizes the quiet periods that allow the females to respond in the presence of reduced noise. However, not all firefly species synchronize their flashes. And in this work, we focus on the properties of the flash patterns themselves and how they may evolve over time to become distinguishable from one another. So on the top right here, you see a selection of a number of firefly species from the Photinus genus found in North America, and their recorded characteristic flash patterns. Each of these gray bars represents separation of a second. And what you see from these are that there's some that are singly periodic, consisting of these evenly spaced flashes, while others are doubly periodic, consisting of this burst of multiple flashes followed by a longer pause. And what are some of the factors that may shape the differences in these different firefly flash patterns? As I mentioned, distinguishability can play a role. It has been observed that for some species which overlap geographically, their patterns tend to be less similar than for those that do not, a case of character displacement. Another factor may be predation risk. So not only does flashing make a firefly more attractive and visible to potential mates, it also makes it more visible to predators, which may exploit that flash signal in order to locate and attack. And in fact, predation pressure has caused some firefly species to stop flashing altogether and instead rely on less efficient methods of signaling, such as pheromones. Other factors may include any energetic costs of producing a signal, although for fireflies, it's believed that this cost is relatively low compared to that of something like flight. Another factor could be the nature of the habitat, in that woodier habitats may, for example, occlude flash signals more readily, as well as female preference. So while males do flash according to a characteristic pattern, there is some individual variability, and across different species, it has been observed that females may prefer males that flash, for example, more punctually, respective to this characteristic signal, while others prefer males that flash more quickly or with longer flashes. In this work, we're going to focus on the first two factors of distinguishability and predation risk, which have been observed to play a role in shaping flash signals, and further explore a trade-off between these two factors and how they affect communication in fireflies. And so to do so, we developed a method called the vocabulary generator, which is a way to simulate co-evolving firefly signals that are subject to these competing pressures to minimize their similarity with one another and their individual predation risk. So this is effectively a multi-agent model where each agent represents a different firefly species, and they all iteratively and simultaneously minimize some cost function, which here we choose to represent a weighted sum of a similarity term and a predation term. And by iteratively minimizing this cost function, starting, for example, from some random initial conditions, the flash signals converge to be distinguishable from one another. And to go into this in a little bit more detail, but for the sake of time, I'm going to keep it rather simple. If you're interested in reading on some further details of this model, please feel free to check out our paper or ask me further questions. So for each step of this generator simulation, each of the sequences can mutate by transposing two adjacent bits or by flipping a bit from off to on or on to off. And the mutation is accepted if it lowers the cost. And again, this cost is a weighted sum of two terms. The similarity term here is represented by the length of the longest common substring to two sequences under a circular permutation, so representing the longest consecutive overlap between two flash sequences. And in this example at the bottom here, these are 10-bit long sequences and the overlap is 4 bits long or 40%. While the predation term is represented by simply the fraction of the sequence that is flashing or on. So here species 1 has a higher predation risk than species 2. Excuse me. And so the predation term could also be representative of something like an energy cost if we chose, because it similarly penalizes greater amounts of flashing. And so this step is looped until the cost reaches a steady state minimum, for example, shown here, and the sequences will ideally have converged to be distinguishable from one another and also individually minimize predation risk. And I will also mention that the weights on this cost function, WS and WP, we can tweak the relative values of these weights in order to explore resulting sequences that have different properties. And I'll go into that in a little bit more detail in a couple slides. So here's an example of how in a system of 5 different species, starting from random initial conditions of these randomly initialized strings of bits of value on or off, they evolve over the course of this vocabulary generator to settle into their steady state sequences. As you can see here, they're also quite different from one another. Some are singly periodic, some are doubly periodic. And by varying the relative values of the weights in the cost function, specifically here we focus on the ratio of WS to WP, we see that, for example, when the similarity weight is much smaller than the predation weight, this penalizes great amounts of flashing. So we see that the sequences are much more sparse. In fact, in this system of 7, 2 of them do not have any flashing whatsoever, which reflects what is observed in nature when predation pressure causes fireflies to stop flashing and rely on pheromones. As we increase the value of WS relative to WP, then the sequences become much more populated with flashing, and this reduces their similarity with one another. One very interesting observation is that we did not explicitly impose the sequences to be periodic or to follow a pattern. As you saw, they were initialized to these random sequences. And by mutating in only a bitwise manner by transposing or flipping bits, we observed that at the end of the simulation, the resulting sequences appear to be periodic or very close to periodic. So in this example result for 7 species, they're very close to periodic and consist of both singly periodic sequences and those with these double flash bursts. We can also quantify the periodicity of these sequences by looking at, for example, the variation in the lengths of the spaces between flashes, as shown in this plot here, with the number of species in the system increasing along the y-axis and the weight ratio increasing along the x-axis. And we find that the periodicity is lower when we have a larger system size and a higher WS-WP ratio. So to conclude up to this point, we've developed this vocabulary generator method to simulate co-evolving flash patterns that simultaneously minimize their similarity with one another and their individual predation risk. And this one potential application for this method is to develop efficient communications in swarm robotic systems that use visible light communication, of which there is a small but nascent body of research. For example, this method could be applied to a self-organization of distinguishable signals in a swarm robotic system, where, for example, the robots may have to adaptively differentiate tasks and communicate in different groups. And finally, I also want to explore a way in which we can use our generator to shed light on how selection pressures may shape the signals of known firefly species. And to do so, we can apply the generator to effectively reverse engineer a cost function that allows us to look at the relative strengths of these selection pressures. And so to do so, we select a clade of related firefly species. Here, this is the 6 species in the consanguineous clade of the North American Photinus genus. And what we do is we run the vocabulary generator along this clade. We sweep over a range of values of the WS-WP weight ratio and find which regime of these weights gives us simulated sequences that most closely resemble the known sequences of these 6 species shown here. And so for these 6 species, for example, one of these has no flashing whatsoever, and the other signals vary between singly and doubly periodic. And we do this a little bit differently. We effectively seed the system with the earliest speciated species P. mcdermidi in a 2-species system. We let that evolve until we reach a branch point in this phylogenetic tree, where we then have a speciation event duplicating the most recently evolved signal. And then we continue throughout the entire tree until we reach an ensemble of 6 different species. And so we perform a parameter sweep over the values of this WS-WP weight ratio, and we observe a regime where the distance between the known firefly flash patterns with the simulated sequences is minimized. And this is an example of one of the best fit firefly sequences that we see here compared with the known ones, which also shows this distribution of both singly and doubly periodic, are rather sparse as well. And this is observed for a weight ratio of 0.5, where the similarity weight is half that of the predation weight. But going forward, we can extend this to exploring cost functions that incorporate other factors that can potentially play a role in shaping firefly flashes, and incorporate other species from the extended phylogenetic tree across the Photinus fireflies as well. So in future work, we can perform further field experiments to, for example, quantify the spatiotemporal resolution that's achievable by fireflies, which will allow us to set constraints on our definition of similarity in flash patterns. We could also reconstruct ancestral firefly signals, and as I mentioned, quantify the relative importance of selection pressures across the full spectrum of different firefly species. And finally, being able to understand firefly communication mechanisms will be invaluable in aiding in worldwide conservation efforts as firefly species across the globe are threatened by light pollution, climate change, and other factors. So thank you all for watching. Thank you to the organizers for having me, and thanks to other members of the Peleg Lab for helping in this work.
Thank you, Chantal. That was a very, very appealing talk. We have a few minutes, 2 minutes. Questions from the chat? I don't see.
I think Hiroki has a question.
Oh,
yeah.
Go ahead.
Thank you, Chantal. It's amazing work, very interesting work. I always wanted to know about fireflies flashing because I have a bunch of them in my backyard. So yeah, I assume this, the whole evolution process also depends on which species coexist in the same ecosystem. Is that so?
Yes, yeah, we do believe so. That would be a driving factor of future work, is to fully be able to combine knowledge of geographical coexistence with the evolutionary history in order to see, how the selection pressure specifically shape those species flash patterns as they evolve. So that's something that we definitely want to consider going forward.
Yeah, in that case, for example, what's going to happen if you change the number of coexisting species from 5 to like a 2 or 10 or 20? Do you see different behaviors arising in this system?
Yeah, well, we definitely, well, it also definitely depends on kind of what values we choose on those weights in our cost function. As we increase the number of species in that system, eventually we will reach a limit, at least for certain choices of that similarity weight, where you'll see kind of at least for a fixed signal length, kind of a degeneracy in the results. We'll see duplicates of flash patterns, which in nature we don't see that many species that have exact same flash patterns. And so it may be unlikely that we'll see kind of so many firefly species coexisting that we see complete duplicates of the flash patterns, but it's possible, at least under the constraints of the model, that it can happen. But that will allow us at least to make some choices on what values we input into the model.
Okay, thank you very much. Very nice work.
Yeah, thanks for your question.
Thank you, Hiroki. Anybody else? I have a question that's more on the light side.
Sure.
My question is, you pointed out that there is one Photinus indictus that doesn't show any signals.
Mm-hmm.
So excuse me, no signal. How does that fit into this picture? I don't understand that.
Yeah, so as I mentioned, I think it's likely that the species would use pheromone signaling in order to communicate with potential mates. Yeah, so there is a great pressure caused by predation on some species to minimize their amount of flashing. In fact, there are even some firefly species that prey on others, and they have what are called like the femme fatales of the fireflies, where they're photourus fireflies that will actually mimic the flashes of their prey in order to lure them in and then consume them.
Okay, I see. I wasn't aware that the fireflies prey on each other. Different species
yes,
of fireflies.
Yeah, some do, yes.
Yeah. Okay, thanks very much. I have a quick question. Seth, you have a quick question. We have time for that.
Okay, thank you. In your model, predation increases with just how much light the fireflies give off.
Mm-hmm.
With real fireflies, do the same species predate all fireflies? They don't care which species or is it that there are species that preferentially predate particular firefly species?
Yes. I think, I would say that there probably isn't like necessarily so much choice. I don't think it's accurate to say that, there may be a firefly that has like a buffet of different species it can choose from. But rather it can be a bit more constrained by like the time of day and the particular location. I think
I know that some species have kind of like a search image, like a predator species has a search image, and that's why they end up preferentially predating a particular species. And I wondered whether the actual pattern of flashes was something that a predator species could also lock onto, and that would be just a different pressure, predation pressure, not stay dark, but don't be the same as the preferentially predated species.
Yeah, I think that would be fair. I think that could be something we can incorporate. It may also depend, for instance, on kind of any signal processing resolution of the predator too, that where certain types of flash patterns may in some sense become more appealing. I don't have too many more precise details, but that's a really great point and something that we could consider if we want to focus on specific species interactions.
Thanks. Really nice talk, I thought. Thank you.
Thank you.
Thank you, Chantal, again for this wonderful presentation.
Thank you.
And we have to move on now. Hiroyuki Iizuka is the speaker on the next talk, generation of complex patterns using coupled generative adversarial networks. Hiro.
Yes, thank you. And I'm Hiroyuki Iizuka from Hokkaido University. And today I will talk about the complexity of patterns created by the coupled generative adversary networks. Okay, and our main question is how complex signal patterns like our human language or syntax of bird songs can emerge. There are so many studies for the evolution or acquisition of languages in ALife so far. And these are the example of synthetic approach to languages with robots and artificial agents. And then not only the robots or simulated agents, but also there is a synthetic approach with the human participants as well. But basically in all those experiments, the players, robots, or agents have the common objective to achieve a task and then try to create the word meaning in shared way. So the basic idea of those studies is that the communication system or language is shaped by imitation and the shared way of using symbols or motions. As a different direction, some studies consider not only imitation or sharing information, but also using the idea of not to be imitated. The first example is the imitation games performed by Suzuki and Kaneko. And they use the logistic maps as the song generator of time series, and the agent with the different nonlinear parameters of the function imitate with each other. And the one who can imitate the other's time series obtained higher fitness. And based on these fitness, the nonlinear parameters are optimized in the evolutionary way. So what the function as a generator has to do is to imitate other time series, and also to generate the time series that is difficult for others to imitate. And then finally, in the end, they show that the time series changes very simple periodic dynamics to chaotic one. So that kind of the imitation and not to be imitated causes the complex patterns. And here is another example. And also the Moran and Pollack shows that under the competitive situation, where one wants to create the same pattern, signal pattern with others, but the other doesn't want to create the same one, but so want to create a different signal pattern. Under that kind of situation, the generator of finite state machine and the time series become complex. So in this way, in the language evolution, all attention is focused only on the imitation and sharing. But some people focus on the competitive situation, and same as then hypothesize that the situation in which they do not want to be imitated or do not want to be shared are equally important to make the patterns more complex and the structures. So we call the situation where the kind of the situation where imitation and not to be imitated happens at the same time, adversary imitation. So individual A want to imitate the others, the opponent's the time series or understand the time series without the opponent imitating their own signal patterns or understand the signal patterns. So in the same way, in the same way, individual B also want to imitate the opponent, and without the opponent imitating the individual the own signal patterns. Okay, and the reason why we focus on the adversary imitation is because it can be evolutionary dominant. So, for example, the ability to imitate the profitable and useful behaviors of others lead to the better fitness. And also this may remove this fitness of the individual B, because they can steal the benefit from the individual B. So so it means that if A is not to be imitated from the B, so A can protect their profits. So so successful imitation and not to be imitated brings better fitness. So it can be evolutionary dominant. So our objective here is to propose the simulation model with a deep neural network that complexifies the signal patterns through adversary imitation learning. And we use the coupled generative adversary networks in which the generation and the recognition networks are separately implemented unlike the previous imitation and linguistic prediction games. And we will show the adversarial imitation learning causes the complex patterns and increasing complexity of patterns through the mutual learning without the need for the evolutionary random processes. And then let me introduce the generative adversarial networks, GANs, briefly. And the GANs consist of generator, a generator, and a discriminator. And then those networks are trained adversarially to produce data that do not exist but look very realistic. So here is a discriminator. So discriminator is trained to distinguish the real data from the fake data created by the generator. And the generator is trained to create the fake data to make the discriminator recognize it as real. So here is the adversarial relationship. So those networks are trained in a competitive way. And in the end, the generator can create a very realistic fake data that do not really exist in the real world, but it's very realistic, right? Okay. And then we use the GANs for our model. And then this is our model where two GANs are coupled for adversarial imitation learning. And I will explain the step by step. And the first, this is the case when agent A generate A's own time series and agent B imitates A's the time series. And then generator A produce the time series in a recurrent way while receiving its own output. And then generator B receives this time series, A's time series as an input, and then produce the imitation time series while receiving the A's time series, right? Like this. And then the discriminator, this one, the A, is trying to discriminating whether the time series is generated by your own GA generator or the opponent's generator GB. So this is the own time series. The DA has to say, oh, this is yes. But in this case, this is the imitation time series. So DA has to say, this is no, right? And then generator A is trained to make it easy for its own discriminator to know it's created by its own. So say yes, right? So this one wants him to say yes. But the generator B is also trained to fool A's discriminator. So this generator wants him to say yes. So here is the adversarial relationships. And then roles are switched and the agent B, so this is the case when agent B generates B's own time series and the agent A imitates the B's time series. And this side of learning is also performed in the same way as explained before. And then here is the overall picture of our model again, okay? And then here are the loss functions, but you don't have to understand exactly. But those all networks are trained with the errors produced here and the backpropagation you used for the training, okay? And then this is a result of the time series, and then yellow indicates their own time series, and blue one shows the imitation time series. So at the beginning, the time series is very simple, but at the end of the simulation, it becomes more chaotic. Okay, and then this is the bifurcation diagram according in response to the epochs. So at the beginning, they produce the simple dynamics, but at a certain point, the dynamics becomes more the chaotic-like behaviors. And then we calculated the Lyapunov exponent to show that the time series really become the chaos, right? So this is the result. So around here, that Lyapunov exponent become the positive. So it's really the chaos. And then this is a return map. So at the end of so they try to imitate with each other, but at the same time, they want to be separated, okay? And then we applied our model to the spatial pattern generators and the discriminator. So this part is the not the time series, but now it's a spatial patterns like images. And then this time that we test the two conditions. One is the mutual adversary imitation learning. So the adversary imitation learning happens. And one is the unidirectional adversary imitation learning. So only the generator B try to fool the discriminator DA. So one side of the interaction, okay? And then this, again, this is a loss function. You don't have to understand that this is a result of the generated spatial patterns. And then this is the unidirectional adversary imitation learning. At the beginning of those networks are initialized randomly, so the generated pattern is very random. But as the learning process progresses, the generated patterns became the increasingly locally detailed and cluttered in unidirectional adversary imitation learning, like this, right? Actually, this is the video. Then this is another example. Now again, the spatial pattern becomes cluttered and the locally detailed. And then this is a result of the mutual adversary imitation learning. And in this case, compared with the unidirectional adversary imitation learning, these patterns appear to have form a sort of the structured pattern. And then this is another example of the results. At the beginning, it's a random, but it looks they try to create the structured pattern. And to show that more quantitatively, we calculated the fractal dimension and entropy. And then in unidirectional adversary imitation learning, the entropy simply just goes up, and then the fractal dimension just stays low. But in this mutual case, the entropy sometimes goes down, and the fractal dimension goes up. Okay. Okay, so my message is that the information non-sharing becomes very important behind the information sharing, same as the Moran and Pratt. And we believe that the adversary communication is necessary to create the structure of the signal, which may have been incorporated into the communication system in a cooperative way. That is the hypothesis and the messages. And then this kind of the situation can be considered that adversary imitation can happen in these situations as well. Yep, this is my conclusion. Thank you so much.
Thank you, Hiro. Very nice talk. And we have a question from Seth, if I'm seeing this correctly. Seth?
Hi, Hiro. Presumably, maybe it would be interesting for a system where each half of the population has access to a part of the sensory space that the other one doesn't. I mean, this would make the problem a lot easier to solve, right? That one network would learn to use part in your 2D patterns. Imagine that one opponent can see the top half of the pattern, and the other opponent can see the bottom half, and they both can see the middle. You know, because you find in nature, don't you, that some species they evolve colors that other species can't see, right? There are beautiful patterns on a moth, but to me it just looks brown. It just looks like bark. And I wonder whether if you gave your populations access to that, they would evolve to exploit parts of the sensory space that the other population can't access.
Yeah, I think it can be if unseen parts, there is an unseen part that they can use that kind of the secret, the information for the same group, the friend groups, and then the adversarial team cannot see it. Then so this code is understood by that kind of the secret information. I think that is a good idea. So I want to test it.
Well, I guess you won't get. The dynamics won't be as interesting because it will just stop, right? It will find that solution and then it will stop. But I think it would reflect something that maybe happens in nature. But yeah, very interesting.
Yeah, I agree. Yeah, thank you.
Okay, I think we are over time now and soon approaching the plenary keynote speaker. So, I see already Sylvia is in the game here. Adversarial or not, Sylvia? You are the one.
Thank you. So at this point, I would say 10 minutes break and see you each other soon for the keynote talk. And I would like to give you one information that we will share again, even before the keynote, even with the people coming from the green room. The proceedings are now online. We will soon share with them here and on the Slack, the link. See you soon.
Bye.